So what we are going to do today is to look a little bit into projective geometry, or especially homogeneous coordinates. I know that most of you or should have attended that already, or have attended one lecture on that last year with Wolfgang Förstner. But as the homogeneous coordinates are kind of central for the remaining part of the course, I thought of giving kind of whatever 60 minutes, something around 60 minutes, wrap up, or introduce them again, wrap up, and present you the most important component that you need to know for understanding the remaining part of the course. So this is just kind of, sees it a little bit as a summary of the most relevant things that we are going to use here. So the first thing is, why are we considering homogeneous coordinates, and why is this something which is important and especially simplifies our life? So we all started, or most of the activities that we do, especially from now on, assume a camera, which we use in order to take pictures, and we want to analyze those images and then do inference about what we see, what the geometry of the scene looks like, maybe where the camera is, and other things. And in order to do that, we need a model for our camera. And the standard model is the pinhole camera model. So just as a reminder, that was kind of this quite simplified model. So, okay, it shouldn't be green. You have a box here, which is your camera. There's a small pinhole, something like this. And you have an object in front of your camera, let's say this tree. And then all rays from that tree pass through that pinhole and generate an image here in the back of the camera. So this ray goes somewhere over here, this one down here, the one in the middle here, so that we get the tree, which is then standing upside down, something like this. And the important thing is that here all rays pass through that center, to this point. So the single point, and all rays from an object to my image pass through this point. And this concept that every ray goes through this pinhole is something which is very important, and that we'll actually exploit in photogrammetry, in the photogrammetry course until Photogrammetry II, actually. And what we now want to look into is kind of what we get here in our image is actually a projection of the 3D world onto this 2D plane. We need to understand the mapping to this plane in order to appropriately describe what we see. So for example, if we have a certain interest point somewhere in our image, what do we know about where these points lie in the 3D world? And if you can look to an image, just a standard image taken from the house, and we want to look into certain properties or geometric properties that hold in the real world, and the question is, do they hold in this image? So for example, if there's a line in the 3D world, is this line actually mapped to a line in this image? What do you think? So if we have a line in the 3D world, is this line mapped onto a line in this image? So you can just, let's say, randomly pick a line, let's say, whatever, this line over here. This should in reality is very likely to be a line. This is something then you can say due to your background knowledge how the roofs are constructed, or that this is probably one line over here, or the bottom line of the house. And this seems to be more or less a line. Also, this is probably a straight line in reality, and is mapped to a straight line in this image. So at least for this image, we can say this is a straight line preserving mapping. So straight lines in the real world are preserved in our image. There are other things. What about angles in the real world? Are angles in the real world mapped to corresponding angles in our image?
Well, I guess not. For example, when you look at the pillar right of the gate, at the upper, exactly, I think that those are all rectangular angles, but they are not on the picture.
That is true. You can see that there's piles over here. So that these are all 90-degree angles, and they're not mapped to 90-degree angles in this image. So we are not preserving the angles that we have in the real world. What about size of objects?
Also not because you have a perspective effect.
So the size of the object differs depending on how far they are away from the camera. This basically determines how large the object is in the image. So two objects of the same size being at different distances to the camera are, of course, mapped at different sizes in my image. So we don't preserve the lengths. This is exactly just a summary of what we have actually discussed here. So at least this image was straight line preserving, so straight line is mapped to a straight line, but the two other properties we said, length preserving or angle preserving, this does not hold for this mapping. Does the straight line, preservation of straight lines is always true for, say, standard cameras or typical cameras? Yes, please.
Well, it's certainly true for such a camera obscura like that, but if you use special objectives, you might get round lines where you have straight lines and the other way around.
So if you use wide-angle lenses especially, or fisheye lenses, you see a very strong distortion. You can perfectly see that on the horizon line, that the horizon line is typically not a straight line anymore, or any other straight line that you see or picture through, for example, fisheye lens or wide-angle lens. But for kind of normal lenses or for the pinhole model, we can assume that they are, or they're very close to straight line preserving. Okay? So if we preserve straight lines, what happens about parallel lines? Parallel lines, lines which are parallel. So I have two lines. So if I go back to my house, if you identify a few lines which are parallel, are they still parallel?
It depends on the direction. If they are going from the left to the right, and they are not going left to the right, they probably stay parallel, or they stay parallel. But if they are an extension going into the distance, then they are not parallel anymore.
So if the plane in which the lines lie is the same, or has the same orientation that my image plane, that's true. If we map somewhere else, this is not the case. So parallel lines may intersect, they may not stay parallel. So I just indicated that by two things which are parallel. So here where the roof starts and the bottom of the house for both sides. So you can see those parallel lines intersect. They don't intersect inside the image, but if a kind of extent that they intersect somewhere outside the image. Okay? So parallel lines in the real world don't necessarily stay parallel. Okay? Okay, what we can do, however, we can actually rectify images. So we can do a rectification of those images. So for example, if I want to measure certain elements on the facade, I can actually rectify the image as if the image plane would be the same orientation than the plane, for example, this wall. I can do that for this wall, and I can even do it for the ground floor. And then I actually can do measurements, these relative measurements in those images. So for example, here seeing the tiles. So those images are generated from this image, knowing something about the geometry of the scene and where the camera is. I can actually generate those rectified images. But I can do the measurement then in the plane. So here on the ground plane, on this side of the wall, or on this side of the building. But I can't do this in any part of the image. But I can do certain rectifications with respect to certain planes that I have in my image. So I can do that, and then this allows me to derive some information about the geometry of that scene, for example, or do measurements in there. So central questions that we are typically addressing, and this all is kind of the motivation of why we're using homogeneous coordinates later on, or introduce them today and use them. So central questions that we're interested in is deriving a relationship or geometric relationship between the objects that we see in the scene and the objects we have in our image. So if we see something in an image, what can we infer about the geometry of the scene, or what kind of images will we generate if we know something about the world? Also kind of often we can't, or depending on kind of what observations I have, I may infer some parts of the geometry, I may not infer some other quantities. For example, for just a single image, inferring something about the depth typically requires some background information, some background knowledge. So maybe I'm also fine with the relationship between the points in the image and the rays to the object. Like the ray going from the image here to the object, and just know that the object basically lies along this ray. I may also be interested in estimating where the camera is. So given I know something about the scene, let's say given I know the geometry of that tree and where that tree is, and I take the picture, can I actually derive from that picture the position of the camera. And that's actually something that we will do in the remaining part of the Photogrammetry I course. So starting with that in kind of next week, how we can actually estimate where the camera is if I know the geometry of that tree just from the picture that I have. Okay, that's what we want to do is, but the problem that we have is that the camera generates a 2D image from the 3D world. So it projects the 3D information onto my 2D image plane. And this causes what we called also in the beginning a loss of information. So we lose some information. We can restore some of this information or estimate some of the lost quantities under certain circumstances. So for example, if I have multiple images, of the same object, I can infer something about the depth information up to a scale typically. Or depending on how much other information I have, if I know some of the locations of the cameras from where they have been taken in an external coordinate frame, I can even resolve some of those ambiguities. I typically need to know some details about the camera. If I know the size of certain objects, I can also infer something about the geometry of other things that I see in the world. So if I have more than a single image, I can actually do more. And that's something which we will see directly in the beginning of the Photogrammetry II course when we look into using stereo cameras or two cameras or two images taken from different locations, potentially from the same camera, maybe from a real stereo setup. So if I take one image of you from this location and the second image of the same scene from this location, I can actually infer something. And I can estimate, for example, what is the movement of the camera. It's one thing I can actually estimate. Or I can estimate what is the geometry of the scene. Or I can actually do both things at the same time. And that's something we will look into how we can actually recover this information. But the most important thing, what we are going to exploit, is basically what I've drawn here, or just illustrated by this effect. So if this is my image, I have the rays going from the image to my pinhole into the real world. And I can just measure those rays. So one of the pixels, one of the points in my image basically represents the information along this ray, and I don't know where along this ray this information is. Only if I have multiple images taken from different locations, like in this example over here, if this is location of camera 1 and camera 2, and by triangulation, if I know the corresponding points between both images, I can actually estimate the depth information. And what we want to look into today is how can we actually describe this projection or this fact that I have a point which somewhere lies along this line in a very nice way. So it's kind of trying to set the focus, and if we now go back and to the previous example that we had, we said straight lines remain straight, but parallel lines may not remain parallel. And one of the examples where you can actually also very nicely see is these classical images of train tracks. So those train tracks are actually parallel, but they intersect somewhere at what is so-called the vanishing point. So somewhere along the horizon there, I have a vanishing point where those two parallel lines intersect. And if I have two different parallel lines, let's say two parallel lines which move in this direction, they have a different vanishing point which may lie somewhere over there. And this vanishing point results from the fact that these parallel lines in the real world don't stay parallel due to the projection onto my image plane. This basically everything is set, so all parallel lines which are mapped intersect at the vanishing point, and the vanishing point can also be something described as at a point at infinity. So it's infinitively far away, and there my parallel lines actually intersect. And every direction in the sense of if I have two or multiple parallel lines, if they have a different orientation and look into a different direction, then they have a different vanishing point. For one direction, I exactly get one vanishing point. And the key thing is kind of these points at infinity. And as soon as we have that, we may also think, how can we actually describe points at infinity? Of course, if we are in the Euclidean space and want to describe a point at infinity, we could actually set the whatever x, y, z coordinates to infinity, and then it's a point which is infinitively far away. But what I lose if I do that is actually directional information. So if I have a point and say, okay, the x, y, z coordinates is, or the x, y coordinates is, for example, infinity, I know this point is infinitively far away, but I basically lose completely track in which direction this point is. So I can't describe the fact like, in this direction over there, the point is infinitively far away. And this is one of the limitations that we have, and this is one of the motivations why the Euclidean geometry may not be the best framework to use if we deal with cameras and if we deal with projections. And this is a reason or motivation for projective geometry, where we say, okay, there's a different formulation for that, for describing the world, and which is well suited or better suited to describe some of the relationships we have and we want to model. And one of the things is actually points in infinity at a certain direction. So it's important to note that the projective geometry is just, let's say, an alternative framework to describe our objects and transformations in the real world. And it's not that we can do better things with this technique compared to the Euclidean world. The only thing is that things typically gets easier. So in the Euclidean geometry, the math can get pretty difficult if I want to do all those computations. And this is not the case for the projective geometry. If we use projective geometry, and one of those ways to actually exploit that is homogeneous coordinates, the math gets typically simpler, and the simplification of the math leads to better insights that we get about the relationships that we have here. The important thing is there's nothing which is fundamentally different in the sense that it's more expressive. So we can still say we can give a direction vector and then have whatever a parameter which runs towards infinity and represent that point in the Euclidean world, but it's simply a much more complicated way of describing that. And this led to the introduction of the homogeneous coordinates, typically abbreviated as HC on the slides, because the word is simply that long. This is one way for improving the situation, and which allows us to end up with having simpler equations as if we would formulate them in the Euclidean world, or the Euclidean kind of framework. And two of the things which are very nice and which is very useful for us are those 2 points down here. First thing is that we can actually describe points in infinity with finite coordinates. So we don't need these infinity values somewhere. We can use finite coordinates and still represent points in infinity. And this makes a lot of the computations much easier. This is one point, and much easier to grasp that we can actually represent the fact that there's something along these lines potentially at infinity. And the second thing is, which is actually pretty useful if you work with transformations, is that using these homogeneous coordinates, we can represent different types of transformations, like rigid body transformations, affine transformations, or projective transformations, using a single matrix. And this simplifies a lot of the activities that we do, because we can simply chain those matrices and just multiply those matrices, and this way chain the transformations, which simplifies a lot of the computations that we do substantially. This is kind of one of the two reasons why life gets easier if we do the computations in this space, and this allows us to get better insights about what we are doing. So it's a framework kind of roughly set, so is everyone clear why we are going to do that using homogeneous coordinates? So our goal is to simplify our life. We can do the things in the Euclidean world, but it's more complicated. Okay, given that we now have different things, geometric objects like points, lines or points, and they can be expressed in Euclidean coordinates or in homogeneous coordinates, I want to introduce a slight notation that actually I will use throughout the whole course, and which goes back to Wolfgang Förstner and also the book that he wrote, so he uses exactly the same notation. So one of the things that we have, if we talk about a point, a line, or a plane, we can actually use these calligraphic letters over here. And this represents kind of the object itself, so the entity, so the line or the plane itself. And we can talk about these guys, those letters over here. If we say that we have a point expressed in homogeneous coordinates, we use kind of this type of font, so non-slanted font, non-italic. And if we go for Euclidean coordinates, you have that in an italic way. And this, at least also for me, it really simplifies life if you stick with, so you will find this notation through the whole remaining part of the slides of the Photogrammetry I and II course. I'm not changing that. That whenever you see something in this font, we're in the Euclidean world. Whenever we see something in this font, we're in the homogeneous coordinates. Whenever something is lowercase, it means we're in the 2D world. Whenever something is uppercase or capitalized characters, we're in the 3D world. Also, it's used to actually simplify, should simplify the understanding of those equations. Okay, it's kind of clear. Also, the difference between whatever the different types of coordinates and the point itself. So we can talk about a point in the space, and the point can be represented in homogeneous coordinates or in Euclidean coordinates. And therefore, this distinction of giving the point a different font, we just described the quantity of the object, so the point, and not its special configuration expressed in a certain coordinate system. Is that kind of clear? Okay. So then we go directly to homogeneous coordinates and look to the definition what homogeneous actually means. So what homogeneous means, so representation of x of a geometric object is homogeneous if x and x multiplied by a scalar represent exactly the same thing if the scalar is unequal to 0. So we have this relationship over here, x equals a scalar, which should not be 0, and x. And this represents exactly the same thing. This is something which is homogeneous. In the Euclidean world, this does not hold. This factor. In the Euclidean world, this equality doesn't hold. You can make whatever. You can make a very simple, stupid example. If you're in the Euclidean world and you have a vector, whatever, 2, 3, and then you can actually say, is this the same thing than whatever, 4, 6, which we can express as 2 times 2, 3. And in the Euclidean world, this is not the case, obviously, because 2, 3 is different than 4, 2. So this is, in the Euclidean world, Euclidean, this is not true, this does not hold. Okay? So the homogeneous property does not hold. Okay, how are we, these things, when you feel it for the first time, it's typically somewhat counterintuitive. So how should such an object actually look like which has this property? How homogeneous coordinates of an n-dimensional object looks like is typically that we say, okay, we simply use 1 dimension more. So we add 1 dimension more. We move from an n-dimensional space to an n plus 1 dimensional space by simply adding 1 new dimension. So if we have our point in the 2D world, so it's small, it's 2D, at this font, so we're in the Euclidean world. It's just given by x, y. So this is what I have in the Euclidean world. When I express this in homogeneous coordinates, I add a new dimension over here. I copy the first n dimensions and add a 1 over here. That's kind of the transition from the Euclidean world to the homogeneous coordinates, what it does. How do we actually interpret this thing in homogeneous coordinates? So to have this kind of equality, if I multiply that by 2, for example, with 2x, 2y, 2, why should that be the same? So all those vectors in homogeneous coordinates represent exactly the same point in Euclidean coordinates. If I take the last component over here and divide all other components by the last component. So x divided by 1, y divided by 1. If this gives x and y, we're talking about the same point. So in this case, it's clear. It's x divided by 1, y divided by 1 will give me a vector xy, which is exactly this vector, so it's the same object. If I now would multiply this vector by 2, so if I would have times xy1 is 2x, 2y, 2. If I now want to map back to the Euclidean world, I kind of take the last component and divide all n components by this component. So this is 2x divided by 2, 2y divided by 2. And maybe, yeah. And this is xy. So this is the same object as xy1, which would be in the Euclidean world again, xy. Okay, so just adding this multiplication of 2, so this is a scalar factor, doesn't change the object itself. So I can do the same thing if I have inhomogeneous coordinates something u, v, w. Say it's the same thing as moving w out of the vector. So it's u divided by w, v divided by w, and 1. And since the homogeneous property, I can simply skip that. I obtain this vector, so I have 1 here or something which is sometimes called normalized. And then u divided by w and v divided by w corresponds to x and y. What we basically do is we add, if we go from the Euclidean world to the homogeneous coordinates, we add 1 additional dimension. And by default, we set it to 1. If we want to represent the same object that the first n dimensions would represent in the Euclidean world. And if then I can do all my computations with in my homogeneous coordinates, and I want to move back to Euclidean coordinates, I simply have to divide all n components by the last component. So again, there's another example. This is exactly what was shown, pretty similar to what was shown before. So this is my element in homogeneous coordinates, and this is a corresponding element in the Euclidean world. Okay? So the next thing is, which kind of numbers are allowed in here, in the homogeneous coordinates? Are all numbers allowed? Can I do all combination of numbers in here? And this is not the case. So what in the homogeneous coordinates we require that not all elements are 0. At least one element must be larger than 0. So that is one requirement. So we can express this if we are here in the two-dimensional world. So in homogeneous coordinates, we have our third dimension. Then a constraint is that not all of the elements are 0 at the same time. Okay? And if I want to directly move back to the Euclidean coordinates, as I have to divide u divided by my third component, I can only map that directly back into the Euclidean world if w is unequal to 0. Otherwise, I would divide by 0, right here. So in the Euclidean coordinates, it's perfectly fine to have a 0 down here. But if this last component is 0, I cannot directly map back to the Euclidean world, at least with finite coordinates. Because I would divide by 0, and that would be kind of infinity here. And this is exactly the way, as we will see later on, how we can actually represent points at infinity. If this value is 0, we can still represent a direction with those two components, but represent that the point is actually at infinity, is infinitively far away. And at that point, there's kind of not the direct relation between the point in homogeneous coordinates and in Euclidean coordinates, because in Euclidean coordinates, due to this division, those values would approach infinity, and therefore we won't have finite coordinates in here. So we can represent points at infinity in the Euclidean world, but only not with finite coordinates. So just in this example, if I have points on the projective plane, which is kind of the space corresponding to the projective space corresponding to the R2. So that means all points which are expressed in Euclidean coordinates as x, y. Then what belongs to the projective space? These are all three-valued vectors like x, y, and 1, just as an example. Just add the component. All points at infinity, which is x, y, and 0. get this 0 over here. But what is not in there and doesn't belong to that space is a 0 vector, 0, 0, 0, because our constraint would be violated. Is that clear? So the only vector which is not part of that space actually is the vector where all components are 0. So the first and the last one. At least one of the components needs to be unequal to 0. And again, this is the reason that not everything can be, or if W is 0, then I have the problem of mapping back to the original space. In homogeneous coordinates, I can still live with a 0 here, and those two elements give me the direction, in which direction the point is in infinity. But if all of them would be 0, I would have no direction and no point I could set to infinity. So you can also, maybe this becomes clear in this kind of illustration. So what we have here, this plane, so the gray plane, is kind of R2, a regular R2 world. So far we were living in this R2 world. And now if we go to these homogeneous coordinates, we have one additional dimension. So we can actually see this as a three-dimensional space. We just add this new W dimension, which is in this example, my third dimension. And a point in the Euclidean world with x and y. So here's an E for Euclidean because the figure used a slightly different notation. But what I wanted to say is that this point in the 2D world corresponds to this line in the 3D world. It's a line which starts at the origin and passes through this plane. And we can also have a point which sits somewhere over here. If I do the normalization so that the last component is 1, which basically means I divide all the components through the last component, what happens actually is that I move this point here back to exactly this point. So for this reason, every point which lies on that line corresponds to the same point in the 2D world. So if I kind of do this divide by W, what this actually means that somewhere along this line, I kind of move the point back over here. Okay? Does this figure support the understanding? Yes, please. Yeah. Nee, genau. So just having this point in here is not explicitly part of the thing. So the thing is I can extend this by another dimension, then go to the next dimension, then I use this O3. So it's still part of the figure. But so this point is not part of the space because what I'm doing, I'm basically representing line starting at this origin. And if the point lies at the origin, I have the line and both points are in the same line and could have any arbitrary line. Therefore, this one is not part of the projective space. So if I visualize the whole thing as R3, then of course I would have this point in there, but the projective space explicitly excludes this point. Any further questions? Okay. What we can do in 2D, we can of course do exactly in the same way also for 3D. The only difference is we don't have 3, we have actually 4 components, and then we can move from the 4 components in homogeneous coordinates back to our 3 dimensions in our Euclidean world. The rest works exactly in the same way. Now these are capitalized characters because they represent an object belonging to the 3D world. I can also define the origins of the Euclidean coordinate system, and they are given by 0, 0, 1. This is exactly this example over here, or I've opened the 3D world 0, 0, 0, 1. This would be always that point which lies within this gray plane. So here, so I just added this figure to that slide. It's a bit suboptimal having the same points over here. So the best thing actually would be to remove that to not cause any confusion, because these are the centers of the Euclidean coordinate frame expressed in homogeneous coordinates, and they have to have a 1 in here because this is the center of this plane. Okay? So do you feel comfortable with points in this world, in this kind of representation? You're all fine with points and homogeneous coordinates? Yes, no?
As long as you don't have to calculate it.
So far, the difference is just, the only thing we say is we just have points along this line. Every point along this line corresponds to exactly the same point here in homogeneous coordinates, in Euclidean coordinates. How we transform those points is something we will discuss later on, if we use our transformations in order to do that. Okay, so if you're happy with points, we can move to lines and see how can we actually represent lines. And if we look back how we can represent lines in our Euclidean world, there are typically three ways in how we do that. There's something which is called the Hesse-normal form, or in German the Hesse form, where you basically specify an angle phi and then a distance, and then with those parameters x and y you can vary as long as this equation holds. The point xy is on the line. It's one way for representing a line. The other thing is the intercept form or Achsenabschnitts form, where you have your x and y over here and you have two parameters x0 and y0 equals to 1 or minus 1 equals to 0, which you can use. Or what's called the standard form or implicit form is you have this expression over here. So ax plus by plus c must be equal to 0. So the kind of important thing in here is that we have always a system, we have always an equation. And we have always an equation which something is equal to 0. So I have a component with x, I have a component with y, I have a constant component, and I have 0 over here. Same thing over here. I have x, some coefficient, y, some coefficient, constant part equals 0. And the same exactly we have in here. So the key insight in here, if you look how the lines are represented in the Euclidean world, is that they all form linear equations which are equal to 0. Okay? So this is clear, because we will exploit that in a second. So whatever representation I use in order to represent a line can be written as an equation which equals to 0, and we have linear components in the x and in the y. Okay? All fine? Everyone accepts this? Okay, now let's see how we can exploit that in order to represent lines in homogeneous coordinates. So this was a point in homogeneous coordinates, x, y, and 1. If you actually go back, you can see that we have an x, a y, and a constant component. Okay, so that's our point here. And then we can actually provide three different vectors L, one's represented in Hesse form, one's with the intercept form, and one's with the standard form, where the first, second, and third dimension takes those parameter values. Just basically took those equations, the part which corresponds to x, the part which corresponds to y, and the constant part, and actually placed them in here. The part corresponds to x, to y, and the constant part. What I now can do is, I can simply take this point and compute the dot product with one of those representations. So I say x dot L, I would compute it, that would give me x times cosine phi plus y times sine phi minus d. That looks like pretty similar like this one. The only thing I'm missing is actually equal to 0. So what I can do is, if I have this kind of representation, I can now use this to formulate a condition under which the point lies on that line, which is x dot product with L equals 0. If this holds, then the point x actually lies on the line which is represented in this way. And I can do this exactly in the same way for the two other forms. So the key insight here is x times L, or x transpose L, L transpose x equals 0 is the key condition for formulating that a point lies on that line. I have a point in homogeneous coordinates. This is a representation of a line in homogeneous coordinates. And by multiplying the point with the line equals 0, I'm expressing that the point lies on that line. So all points for which this equation holds are actually points which lie on that line. So they define the line L. So this is kind of clear what we have done. So okay, we start with a point in homogeneous coordinates. We take the equation that we know from our Euclidean geometry on how we can represent lines. We just pick one out of them. And then we say, okay, we have to combine the point and the line in a way so that we can have an equation which is equal to 0, because then we have the correspondence to the Euclidean world. We obtain that by saying x transpose L equals 0, or the other way around. Okay? Okay. So what we can derive from that is in the homogeneous coordinates, we can define a line in the 2D world as a three-dimensional vector, L1, L2, and L3. And again, I have the same constraint that not all of them can be the null vector, because then it would hold, obviously, for every x, y I put in there. And this corresponds to the representation of the Euclidean world, which is the standard form over here. Okay? Now what we can do is we can actually very easily test if a point lies on a line by just taking my representation of a point, my representation of a line. I simply do the test if x transpose L equals 0, then the point lies on that line. So if I have a point in homogeneous coordinates, I have a line in homogeneous coordinates, just by computing the dot product and testing if the result is 0, I know if the point lies on that line, which is nice. Everyone happy with this test? Has everyone understood why we ended up doing this test? So we looked at the equations we know from the Euclidean world. Said, how does a point look like in homogeneous coordinates? How do I need to build up a line in homogeneous coordinates? So I just need to multiply them, and if the result equals 0, I exactly have the equation I know from my Euclidean world. Okay, so next thing we can do, so far what we did, we checked if a point lies on a line. The next thing we can do is we can simply take two lines, and would be interesting, do they actually intersect? So I now have a line L and a line M. I want to intersect those lines, and they should intersect at some point x. This is what this means. So L intersected with M will give me the point x. The question is now, how do I find such a point? How do I find the intersection of two lines? And I want to exploit what we just learned. So we learned before, if I want to test if a point is on a line, I can do it in this way. The question is, how can I now specify that two lines intersect? Because they should intersect in one point. What can we do in order to formulate that?
Make an equation with two of these scalar products on each side of the equation.
Yep, exactly. It's as easy as that. So we say our point where they intersect, transposed L, should be 0, and x transposed M should be 0. This gives me a very simple system of linear equations which I could solve. We can do exactly that. Say L times x and M times x should both be 0. So this boils down to actually solving this system of linear equations. So how can I solve such a system of linear equations? Actually, one of the things how you can do this is actually the Cramer's rule, which is very easy to use for small systems like 2x2 systems. which actually says if I have a, does everyone knows grammar rule, or should I explain that again?
Theoretically, yes.
Everyone knows that? Okay, at least a few people say no. Okay, just to explain easily how that works. I have a system AX equals B. And I can say then the first component of X, of my solution X, is given by the determinant of a matrix AI, we'll explain that in a second, divided by the determinant of the matrix A. So A is this A, and AI is the matrix A where I replace the I's column by the vector B. So you can actually even do a small example on the black. Well, should I do an example on the blackboard? How to apply that? Okay. So what I basically have, I have L1, L2, M1, M2 times X1, X2 equals minus L3 minus M3. So this is what I want to solve. Now let's go to a concrete example. Let's say L equals 1, 2, 3. Sorry, I have to continue with no white chalk anymore. And M is 2, 0.53, for example. So what I then need to do is X, what the grammar rule says me, X1 is that determinant of A1 divided by determinant of A, which is the determinant of A1. I take the first column, replace it with those elements. So it's minus L3 minus M3 L2 M2 divided by determinant of L1 L2 M1 M2. And now I can actually fill that with numbers. So this is the determinant of minus 3 to minus 3, 0.5 divided by determinant 1, 2, 2, 0.5. And if I now compute that, I get the result of minus 1.286 in this example. I can do exactly the same thing for X2, except that I compute the determinant of A2, that A over here. So get exactly the same result, except that I don't replace the first column but the second column over here. And then in this example, you should get for X2 minus 0.857. If you compute that now. Okay, so that's the way how we can actually solve that system. So this system can be solved through the grammar rule by x, which corresponds to my x1 over here, is d1 divided by d2. So this is determinant of a1, this is determinant of a. And same for y with determinant of a2, determinant of a. And the determinant can simply be computed using these equations. Let's take this guy times this guy plus this guy, minus this guy times this guy. And then this gives me exactly those equations, and you can actually compute that. So the interesting part comes now when I say what I've written in here, so x and y, the solution, can be expressed if I write this as a vector. All right, xy is 1 divided by d3, d2, no, d1, d2. I can actually write it in this way, right? This one actually get this result. I can also, sorry. Yeah. What I now can do is, why not simply extending that a little bit, adding D3 over here, and a 1 over here. Right? And then, okay, now my 1 over here, my homogeneous coordinates. What I can do is in homogeneous coordinates, I can drop any factor that I have before that equation. I can throw that away. So okay, my point xy corresponds to those elements. D1, D2, D3. And they're computed exactly in this way. And this is, by coincidence, exactly the way how you compute the cross product. How you compute the determinant in the 2D world gives you exactly the cross product over here. So the interesting thing is now, if I want to compute the intersection of two lines, M1 and M2, that basically boils down to computing the cross product of the two lines, and this gives me directly the intersecting point. Just by applying the Cramer's rule, not on the numbers, but just with the variables in here, I can actually make this transformation. So I can create my new vector, which consists of x, y, and 1. I put the numbers in here, get 1 divided by d3 out, drop that because of the homogeneous property, and then these are the remaining components of my vector. And this, so this, solving this equation, L cross product M, gives me directly my intersecting point x. So instead of requiring me to solve this system of linear equations, I just can execute the cross product and I have my solution. So it's great. That's pretty simple. So if a point x is defined as the intersection of two lines, I can actually compute this in this way. So it's a very, very simple way for computing the intersection of two lines using homogeneous coordinates. Okay, what else could we do with lines and points? We can take 2 points and fit a line through those 2 points. It's the next activity we can do, which we may often need. And happily, we also have an easy way for doing that. So consider we have a point x and a point y. So this x1, x2 is the coordinates of the first point, and y1, y2 are the coordinates of the second point. And I want to compute the line L, consisting of L1 and L2, or L3 in the homogeneous coordinates then, that actually connects both of them. How can I do that? So I want one line which intersects with 2 points.
Well, now we just did a subtraction between the 2 points by coordinates.
But that's nothing.
Is the vector?
That's not what I want to do. So consider the solution we just derived so far for computing the intersection of two lines. What we had a very similar situation. We said we want to have 2 lines and they should intersect in 1 point. We formulated a system of linear equations to solve that problem. Now we have the situation we have 1 line and 2 points. What we can do is we can actually do exactly the same thing. We can simply say my line should intersect with the point x, and my line should intersect with the point y, and again, formulate exactly the same system of linear equations. Solve that, and we're happy. We can do basically exactly the same thing. So what we do is we say, okay, x transposed L should be 0, and y transposed L should be 0, because these are my 2 points through which I want to fit L. So I can set up my system with the Cramer rule. Now I have my L1 and L2 here, the things I want to determine. I have also L3 sitting in here, but I ignore that for a moment. So I can simply just, as we did it before, apply Cramer rule saying L1 is D1 divided by D3, L2 is D2 divided by D3, exactly applying Cramer rule as we did that before. The only difference compared to what we did before is kind of we have the L sitting in here as our factor. But that's not bad. That doesn't hurt us at all. We can do basically exactly the same trick as we did before. We say, okay, we have L1 and L2. So we add in a third dimension L3, which is, the third dimension is L3 times 1, which is D3 divided by D3. So I set up my vector L, saying D1 divided by D3, D2 divided by D3, and L3, D3 divided by D3. The first thing I can do is, as in D1 and D2, I have my L3 in here as well. Right? So I can actually move that out. Move L3 divided by D3 out of the vector. I have that here. And then just the remaining parts form this vector over here. And again, this vector looks pretty much like a cross product. And if I inspect that, we say, I actually realize that this is given by the cross product of the points, of the three coordinates of the points x and y. This is basically more or less exactly the same on what we did over here. Moving this 1 divided by d out, the only difference is we move L3 divided by D3 out. And then through the homogeneous property, I can actually drop that factor because it's just my scalar lambda. And then the only thing remains n1, n2, and 3, which are the three components resulting from the cross product. So I can use the cross product of 2 points in homogeneous coordinates in order to obtain the line which connects those 2 points. Also something which is very easy. So kind of to summarize what we have seen so far. We can very easily test if a point lies on a line, and this holds if this condition is satisfied. We can also say, if we have 2 lines, when I compute the intersection of 2 lines, we can do that very easily. And if we want to have 2 points and connect those points through a line, we can also do this exactly in the same easy way. So it seems to be a framework which allows me to do some of these geometric operations quite easily, in a quite easy and intuitive way, which is nice. Also one of the reasons why using homogeneous coordinates is popular. But one of the things which is very important for us as we work with cameras are actually points and lines in infinity. So we said before that we want to be able to represent points which are infinitively far away but in a certain direction. And I just told you that homogeneous coordinates offer us the possibility to do that by setting the last coordinate to 0. So we are still maintaining the direction, the first n dimensions, and putting the last one to 0, move this point infinitively far away. So we have this thing which is called points at infinity, or sometimes written x infinity, which is the point with 2 coordinates here, and they should not be 0. Both of them cannot be 0. Only one can be 0. And the last component is 0. And it allows us to represent a point at infinity by only using finite coordinates. So we don't have any infinity sitting in there. This is kind of one of the big advantages, because at the same point in time, we can say we have a point which is infinitively far in this direction. I can maintain this direction information. And this is a very, very useful thing for cameras, because what the camera basically does, every pixel corresponds to a direction, but I have no idea where along the line this point actually is. And I can represent points which are infinitively far away. And of course, if I want to map back to Euclidean coordinates, if this last component is 0, I will get non-finite or infinite coordinates in the Euclidean world, because I cannot explicitly represent that with finite coordinates in the Euclidean world. Okay, so let's have a look to those points at infinity. We said we have these parallel lines which intersect in infinity. Let's look how intersections at infinity could look like. So all lines L for which this equation holds, so L dot product, oh, that's actually not written in a nice way, so this should actually be written in a different font, because these are the objects and don't have the dot product between the objects, so this should be in homogeneous coordinates. Equals 0, that means that all lines for which this equation holds, they actually pass through the point in infinity. As the last component of this point x is 0, I can ignore the last component of L, because we anyway set it to 0. So I have my u and v with dot product with cosine and sine of the direction of the line. If I use the Hesse form, should be 0. So independently for the equation of L, what the last component is, all of them meet at that point in infinity. So any line with cosine phi, sine phi, and here an arbitrary value is a line which intersects at this point in infinity. If we now look to this equation over here and look to the interpretation of the Hesse form, the phi specifies the direction, so the direction of the line. And this just specifies what's specifying the distance. So distance doesn't matter. The only thing which matters is the direction. And every line where the first two components look like this, that means all lines which look into the same direction meet at the same point at infinity. And that's exactly what this picture of the vanishing point was actually showing us, that all parallel lines meet at one point in infinity. You can also see that by saying, okay, let's simply intersect two parallel lines with the framework of intersecting lines on what we learned by cross product. So we can say, okay, let's simply say L, M over here. We said, okay, we have two general lines, but these lines should be parallel. So the first two components should be the same. So if A, B, B, and then C and D down here. And what this gives me is gives me the intersecting point. So we can do a little bit of math like this, and the important thing is this expression known here. AB minus AB gives me 0. So I obtain this expression where I have some value over here and some value over here, and this only depends, or this depends on the directional components, but also on the distance between those points. Okay, this gives me the direction, but the point is at infinity, because it has a 0 in the last component. So all parallel lines meet at infinity, and this is something what you can kind of illustratedly see here. If all parallel lines that would have another parallel track here, another parallel track here, they would actually meet at the same point at infinity as long as they are parallel. If we would have different parallel lines like those bars over here, they simply meet at a different point at infinity. They meet somewhere over there. They all meet at one point at infinity. So is this kind of clear? We say parallel lines intersect at infinity. So there's no intersection between parallel lines in this framework because we have an explicit representation for points at infinity. It's nothing which I can arbitrarily introduce. It's something which naturally comes out from the equations of how to compute the intersection between two lines or parallel lines. Okay? Okay, infinitively distant objects or something. If I say, I have my infinitively distant point, which has this form over here. And I can also have an infinitely distant line. I'll show in a second how it looks like this, called the ideal line. This ideal line is a line which has 0 components over here and 1 down here. And what this line is, this is the line where all points, all infinitively distant points lie on. So how to compute if a point lies on a line? Just by the dot product. So we take this point, independent of u and v, with this vector over here. The first component will always be 0, the second component will always be 0, and the third component will always be 0. So, and therefore, it is 0, and therefore, all infinitively distant points lie on that line. So all points at infinity, independent of their direction, lie on this line. So the only interpretation now you can see that actually this is going to be your horizon line at infinity. All points at infinity lie on this ideal line. That's exactly how you can see that. The ideal line is given through this equation. So independently on where the point is at infinity, it will always lie on that ideal line. You can actually see or interpret that as the horizon line, the infinitively far horizon. We can actually do the same thing also for 3D objects. You can say, okay, we have the 3D point, which now has 4 components over here. And we can, instead of a line, we have our plane, which just has 1 component more. Again, something we can do in exactly the same way how we did that before. We can do exactly the same thing. A point lies on the plane, 3D, if a dot product x equals 0. So all the derivations work exactly in the same way as we have done that here, in a very analogous way. And then we can also have our points at infinity. We have also kind of have this ideal plane. We can actually illustrate that. So if this is the person, we're sitting here in the center of our coordinate frame. We have our lines in here, all the different lines, all the things at infinity. So this is kind of your horizon line. This was the ideal line going around here. And this is kind of then the plane, like whatever, the sky. You can actually see that as this ideal plane. So this is kind of the analogy to the things at infinity. But what we are mainly using here are actually the points that we have at infinity. So being able to represent points at infinity. So one of the big advantages that we have. The second big advantage is transformations. That was the second point I had in the kind of positive list for the homogeneous coordinates. And that was that we can very, very easily deal with transformations. So projective transformation, so transformation in our space that we have, is an invertible linear mapping which maps, this H, the mapping, which maps x to some other x prime. And one of the key, or what is called the fundamental theorem of projective geometry, tells me that every one-to-one, so one-to-one is an injective function, straight line preserving mapping is a projective space Pn on itself, is an homography for any n larger or equal to 2. What it basically implies, or the important thing is, that all one-to-one straight line preserving mappings, and those were the mappings I'm actually interested in for my pinhole camera model, are linear, is a linear function, so thus can be expressed with a single matrix if we use homogeneous coordinates. And that's the reason why I can actually describe then in this simple form, because everything can be put into this matrix H. So the general projective mapping has exactly this form. And what I now want to do is, I want to look into these different instances of H which are possible and see how we can describe different types of transformations. So the most easy form is a translation. Let's express a simple translation through this matrix H. And this is also one of the big advantages compared to the Euclidean space, where I can perfectly express my rotation with a matrix, but not a translation. I always had this plus a vector. If I move to this n plus 1 dimensional space, I can do this much easier by setting up our matrix H. So it's an arbitrary scaling factor, which I don't care, because this is part of the homogeneous property. And I have a matrix, so this is now for the 3D world a 4 by 4 matrix, where this is a 3 by 3 identity matrix, this is a 3 vector, this is a 3 vector transposed, and a 1 over here. So exactly as it is written over here. Then this means this is a rotation which is expressed typically here, but it's an identity, so there's no rotation involved. I have a vector which translates along x, y, and z. And I build up this matrix H, identity here, 0 here, 1 here, and here we just have a vector of how much I want to translate in x, how much do I want to translate in y, and how much do I want to translate in z. And this mapping actually performs a translation of the point by tx, ty, and tz in the corresponding dimensions. So this point is translated through this transformation, gives me the new point. So x prime is a translated variant of the point x. Nice thing is, this is just a matrix product. So I can actually add a second matrix over here. Let's say I apply H twice. H, X would be simply two translations by exactly the same distance Tx, Ty, Tz. Other things which are important, rotations. I want to express a pure rotation. I put here a 0 vector of dimension 3, because this I don't have any translation, and I replace my identity matrix, which was sitting over here, by a standard rotation matrix. So standard rotation matrices, as you know them, expressed in 2D or in 3D, rotation around the x-axis, y-axis, and z-axis. I don't want to go into the details. You've seen that already. You just take your standard rotation matrix and actually plug it in here. That's it. And then you have kind of this type of transform, which has 3 parameters, and these are the rotations around the x-axis, the y-axis, and the z-axis. Now we can actually combine those. We can look into the translation and a rotation. This is something which we typically call a rigid body transformation, which has 6 parameters, which involves translation and 3 degrees of freedom for the rotation. And I have my rotational part over here and my translational part over here. And then I can, step by step, add additional parameters and make new transformation which have different expressiveness, powers of expressiveness. So what I can do is I can now add a similarity transform, which is a rigid body transform plus a scaling with 1 degree of freedom in terms of scaling. I can do that by simply adding a scalar m over here. So basically scaling my whole system, make it larger and smaller, rotation and a translation. The important thing in here is this scalar is not supposed to sit in front of this matrix, because then it would be eliminated through the homogeneous property. I'm only allowed to scale the first 3 dimensions. And the key trick is to not scale the 1 down here, because if this would be scaled, this would simply go away through the normalization. So the similarity transform is an angle-preserving transformation. We can also look to affine transformations, where we have, in addition to the similarity transform, we actually have 3 scale parameters, not only 1, in the different directions, and we have a 3 shear parameters for shearing the system. Through the shear, we don't have an angle-preserving mapping anymore, but we are still have the fact that parallel lines remain parallel. So with the affine transformation, we have an angle. It's not angle-preserving anymore, but things which are parallel before are parallel afterwards. So this matrix A here is a 3 by 3 matrix, which takes 9 degrees of freedom. This takes 3 degrees of freedom, which gives me 12 degrees of freedom. So this matrix A is a general matrix, no constraints on that matrix. And the only thing which is left now here, where I have some 3 degrees of freedom left, are those zeros over here. And the next step, in terms of generality from affine transformation, is then the projective transformation. The projective transformation eliminates those zeros over here. So here we have a general vector A, which are 3 additional degrees of freedom. So it's a affine transformation plus the 3 parameters. And these 3 parameters are those parameters or part of the projective transform, which are the reason that parallel lines may not stay parallel. This is what happens in the projection. This is what we have seen in the image I showed in the beginning of the house, where you have your parallel lines and they're not parallel anymore. Because through the projection of the pinhole model, we have elements in here which are non-zero. Okay, there's also a small list for 2D, what kind of different type of transformations we have, how the original figure looks like, how the transformed figure may look like, and how the H matrix looks like at the individual parts and written in this compact way. Then you can see here the most general one, which in 3D has 15 degrees of freedom, in 2D has 8 degrees of freedom, that those parallel lines here are not parallel anymore through the projection. We can do the same thing for 3D, and what we basically have, we have this type of hierarchy. We have translation and rotation, which has one or, so rotation, one parameter in the 2D world, 3 parameters in the 3D world, or translation by XY or XYZ. If I combine both, I get the rigid body transformation with 6 degrees of freedom in the 3D world and 3 degrees of freedom in the 2D world. We have the similarity transform, which is the rigid body transform plus the scaling, one scale factor. Then we have the affine transformation, which has different scalings and the shear. And then we have the projective transformation, which has all the degrees of freedom. So 15 for the 3D world, we have a 4x4 matrix, and the only degree of freedom which is missing is due to the 1 in the lower right corner, which is the homogeneous property. Therefore, I have only 15 degrees of freedom, although I have 16 elements, but one element is forced to be 1, or depending on the scalar factor. It can always be normalized to 1. So all these different types of transformation I can express with linear mapping in this projective space, which is really nice. And since it's a linear transform and I can use the matrix to actually encode that, I have the very easy way for chaining and inverting transformations. So if I have this transformation, I want to get the inverse transformation, I just need to invert my matrix H. By computing the inverse of my matrix H, I directly invert this transformation. So I just need to stupidly invert my 3x3 or 4x4 matrix and have the inverse of my transform. And I can also easily chain them up. So I have transformation A2 and A1, I can execute them one after the other of the vector x and get my new result. Remember, the matrix multiplication is not commutative, so if you swap them, you may end up with a different transform. So this doesn't have to be equal. But the ability to change those matrices really will simplify our life. If we have a large set of different number of transformations I want to execute one after the other, it's just a product of matrices, which I can very easily write down and compute. Even can combine all of them into one matrix, and then one matrix encodes all the transformations of the individual matrices. And also being able to invert them, the transformation, just by inverting a matrix simplifies life substantially. And this brings me to the end of my, tour through projective geometry and homogeneous coordinates. And the kind of key things as a take-home message is that the homogeneous coordinates are just an alternative way for representing geometry. And they have a few advantages. The advantages are that they can typically simplify mathematical expressions. We can explicitly represent points at infinity with finite coordinates. And we can very easily define the transformations that we have seen here, so the projective transformations, in matrix form, so we can invert them easily, chain them in a very easy manner. And this substantially simplifies the mathematical equations that we typically face and have to deal with. We can represent points at infinity. Yeah, that's what I said. And how homogeneous coordinates actually realize that is that they add an additional dimension. And this additional dimension is used for normalization, for normalizing the other components if I map back to the Euclidean world. And by setting this normalization to 0, I have the chance of representing elements or geometric elements at infinity. And the only how homogeneity is actually defined through this equivalence. So an object is homogeneous if x equals a scalar times x if the scalar is unequal to 0. So I'm somewhere along in this space, I can see this, I add a new dimension, and there's somewhere along this line in this n+1 dimensional space where this space intersects with the n-dimensional space where the last dimension is 1. This is actually the corresponding point in the homogeneous coordinates. So being familiar with using homogeneous coordinates in those transformations is something that you will need to do through the remaining part of the course and through the Photogrammetry II course for at least 50 to 80% of the course material. So make sure you are familiar with that. There will be an exercise about homogeneous coordinates as well, so that you're kind of familiar with using them if this is not already the case. There's also, Wolfgang Förstner's script gives you a very good summary about what has happened here. I'm used exactly the same notation as in the script, so I can strongly recommend it. That's it from my side. There are no questions. Thank you very much for attending, and from day after tomorrow, we will start with looking more deeper into cameras, into intrinsic parameters, extrinsic parameters of cameras, and how we can actually describe the mapping from a point in the 3D world to my image. Thank you very much.